Okay, sorry. So I had to stop that rather abruptly, but it doesn't matter. So we were looking at this figure, which is showing zonal winds and sea surface temperatures. These are anomalies along the equator, so the mean climatology has been removed so that you can see the signals much more clearly. And the dark shading here and the solid contours indicate westerly wind and high SST anomalies, etc. But the main point you want to see is that there are relatively high frequency forcings in the zonal winds, the anomalies in the zonal wind, and they are mostly on the western side of the basin. If you already have been exposed to things like westerly wind bursts in the context of El Nino, you know what we are talking about. But if you don't, no problem. You can go and look up my podcasts on El Ninos in the other courses. But here, you just need to focus that there are in fact sub-seasonal or intra-seasonal signals in the winds. How they are generated is a more complicated question, but often they are related to Madden-Julian oscillations, which are again the inter-seasonal variability. But you can see that the signal here is doesn't have as many sub-seasonal, intra-seasonal variabilities here. So you do see a signal that starts, so time is going up this way. So there is a first one. These then, there are reasons why they start here and then extend eastward. Similarly here, because the ocean is being forced with waves, which then generates a thermocline response, which then generates a sea surface temperature response, and then there is a coupling between these high frequency forcings and low frequency response of the ocean atmosphere system, in fact. And that's what we are looking at. So the 97-98, if you don't know, probably was one of the biggest El Ninos on record after 1982-83, and then we had one in 2014-15. So you can clearly see that these kinds of forcings in zonal winds, which project very effectively onto waves in the deep tropical Pacific or deep tropical ocean, because the Coriolis goes close to zero, and then you have equatorial responses as well. So the eastward propagating signal typically is Kelvin wave, and there are also advection. So these high frequency forcings also generate wind-driven currents, and because it's being pushed eastward, you add your Coriolis being deflected to the right in the northern hemisphere, to the left in the southern hemisphere, and you get a convergence, so you get pushing down of the thermocline because of that as well. The net impact is this kind of growing response in terms of very strong sea surface temperature anomalies. During an El Nino, you expect warm temperature anomalies in the central eastern Pacific, even though more recently we have had many warmings happening around the dateline and so on. So in terms of the ocean and intra-seasonal variability, this is the mechanism by which the low frequency rectification is generated. Here is another example of zonal current illustrating the subsurface. So here we are looking at the meridional section around the equator. So here is the equator. You're going from 4 south to 3 north. So you have the meridional scale of the currents being shown here. So near the equator, let's see, hatching and solid contours indicate eastward currents. So these are positive. These are dark shades with negative numbers, so they are westward currents. So these are zonal currents. So imagine that you are looking across the equator and the currents are east-west. So the meridional structure of the winds is seen here. So again, you see these kind of stacked jet kind of structure here. So you have eastward currents, westward currents, and eastward currents, and then again westward currents, and so on. So this kind of a response can be generated without going into details. The waves that travel eastward, Kelvin waves, also propagate downward and take some energy down, or then the energy comes back up, and all kinds of details are there which I'm not getting into. But the main thing to remember is that the ocean generates lower and lower frequencies. This is showing now the time evolution again for 1991 and 1992, going from the western Pacific towards the east. So time is going this way, so this one is eastward propagation in this direction. So we are looking at anomalous depth of the 20 degree C isotherm along the equator. Dark shading indicates deep anomalies with a contour interval of 10 meters. Intra-seasonal Kelvin waves are evident as tilted bands, so they propagate relatively fast. They can cross the tropical Pacific from west to east in about 3 months, so that's basically intra-seasonal time scale. That's why you don't see a massive tilt here. But if you looked at the same thing in Rossby waves, you will see a much bigger tilt because they propagate much more slowly westward and so on. So this is the temperature, the impact of these Kelvin waves that you are looking at in typically in sea level heights, sea surface height anomalies. But here we are seeing it in terms of the depth of the 20 degree isotherm, which corresponds to the sea level anomaly as well. You can see the impact here. So here is the sea level anomaly again, looking at 0 degree 140 west, so equator and 140 west, which is somewhere here. So we're taking a section here, so showing time but depth along that longitude. And here you can see the arrival of the Kelvin waves appearing in the 20 degree isotherm, which is what we are showing here. So again, you see the lower frequencies of seasonal to interannual signals, frequencies being generated by Kelvin waves, which are in intra-seasonal time scales, which themselves are forced by zonal winds, which are literally in bi-weekly time scales. Okay, so this is an example of interannual amplitude of intra-seasonal outgoing long wave radiation averaged between 5 south and 5 north. So that's a deep tropical band, defined as 1 year running standard deviation of intra-seasonal band-passed OLR. Outgoing long wave radiation is a good indicator of convective activity in the warm waters. So this is in the 60 east, so we are in the maritime continent band here. So we are going into the central eastern Indian Ocean, into the maritime continent, into the West Pacific, and you can see the eastward propagating signals that are typically associated with El Nino. The convection is moving eastward, so 96, 97, 98, starting here, extending eastward, starting here, extending eastward, and so this is the 82, 83 El Nino here. And you can see here in the other plot, amplitude in the global tropical strip centered on the major region of variance at 100 degree east, which is in the eastern Indian Ocean. The abscissa extends around the world, so we are going from Atlantic back into the Atlantic here in the deep tropics. Here we are looking at time series of the outgoing long wave radiation amplitude averaged over the western Pacific, so 150 east to 180 degree dateline, compared with the southern oscillation index. The year ticks on the panel are January 1 of each year. So what this is showing is that the southern oscillation, which is the pressure difference between Tahiti and Darwin, which is basically an indicator of El Nino, shows that the east-west movement of the convection as seen in the OLR anomalies is highly correlated with the SOI, because as we saw before, the entire process of westerly wind bursts, Kelvin waves, thermocline, dipping, surface temperatures warming, convection moving eastward with the warmer temperatures, and so on, are highly related to each other, and that's what we call El Nino. And El Nino is in fact a coupled phenomenon. This is just another example showing OLR at 165 east, showing the annual cycle, lower frequencies, and intra-seasonal timescales. Zonal wind at 165 east at the same location has the lower frequencies, but the annual cycle is weaker in the west, and intra-seasonal amplitude is larger. These are basically variance preserving spectra. Okay, so this is the 20 degrees centigrade isotherm depth, or the thermocline proxy for the thermocline at 140 west, which is in the east. So you can see a phase lagged response, which is corresponding to the zonal wind anomaly here, and the forcing here that produces a signal over here with a lag. So the Kelvin waves produce a signal there that we saw here, for example. Okay, so these are just consistency checks. These are the zonal currents which are strong under the winds, and the OLR where the convection is. So that's the annual signal, but the intra-seasonal signal is here, here, and here. So you can see how the forcing at the surface is related to the subsurface response, and how the timescales lead lags work, because the signal in the ocean is traveling as waves, which is going to create a lag. The Indian Ocean doesn't have as much data as the Pacific, so that's why we started with the Pacific Ocean. But in terms of differences, you can see that the Pacific Ocean has, if you look at the zonal wind stress, strong trade winds, so easterlies, northeasterlies, southeasterlies. And in the west you transition to basically monsoonal forcing, and there is a similar behavior in the Atlantic, which is slightly different because the zonal extent is smaller, whereas the Indian Ocean is dramatically different. You see westerlies here and tapering off into easterlies at the western end. And the thermocline tilt that I mentioned is very clear here. Shallow thermocline, divergence of winds, upwelling, and thermocline is lifted. Cold waters are brought closer to the surface, whereas in the west water is piled up and thermocline is deeper. So we looked at the forcing and the response here. Atlantic has a similar structure, whereas the Indian Ocean has a relatively flat 20 degree isotherm, but the more clear indicator of a thermocline or a sharp gradient in the Indian Ocean is probably the 24 degree isotherm, which has a west to east tilt rather than the east to west tilt in the other oceans. But when you look at the response of the wind forcing, Indian Ocean is of course dominated by the seasonal reversal of the monsoonal forcing. So the currents here, seasonal cycle of the ocean surface currents in February, the westerly easterly winds are northeast winds are producing currents that are westward from east to west, whereas in May you get very strong eastward jet called the Wertke jet, and you get a similar eastward jet in November. So this is called a spring Wertke jet. It's called a fall Wertke jet. Those are very much intra-seasonal timescale variability in the Indian Ocean, and the inter-monsoons during February and August is of course the summer monsoon. May is more, or November is more the inter-monsoon. So you can see that dramatic changes in the surface current structures corresponding to the southwesterlies and the northeasterlies that change with time. And you also have very strong upwelling starting in the southwesterly phase of the winds that generate all sorts of eddies and intra-seasonal timescales here. There is also intra-seasonal timescale variability being generated off of the tip of the Madagascar. And it turns out that because of the wind stress curl, the most interesting region in the Indian Ocean is actually in the southwestern region where the thermocline is lifted up, because the thermocline is not lifted up here unlike the other two tropical oceans. So that we will see in a chapter by Duval, which looks more at the intra-seasonal variability in this region in the Indian Ocean. Okay, so this is the root mean square of the band passed sea surface height from the satellite Topex Poseidon, and basically it's filtered for 35 to 85 day half power, and the data is from 92 to 2003, January to July, doesn't matter. But the main thing is that in the ocean, intra-seasonal variability is high here in the ITCZ, intertropical convergence zone region, in the subtropical front, in the westerly Western boundary currents, the Kuroshio and the Gulf Stream. There is also retroflexion of the North Brazil current. There are winds coming in the gap here called Tehuantepec and what's the other one? There are gap winds that generate intraseasonal variability as well. Indian Ocean has interactions with the eastward propagating Kelvin waves associated with the Wertke jets coming down as Kelvin waves, interacting with the Indonesian through flow that is coming through here, generating barotropic and baroclinic instabilities depending on the season, and generating intraseasonal variability in the thermocline and the sea surface height. This is the instability of the low latitude jet that we mentioned in terms of the Somali current that's crossing the equator and then becomes unstable and sheds eddies and generates intraseasonal variability. So not always directly related to intraseasonal forcing in the atmosphere. You get some variability related to similar phenomenon here as well. And of course the Southern Ocean, these are the western boundary currents in the southern hemisphere, but there is also Southern Ocean, which is very stormy and has lots of instabilities in the ocean that project onto intraseasonal timescale. So available potential energy that gets converted to kinetic energy of the currents, thermocline, sea surface height, and so on, based on various processes project onto the intraseasonal timescale. So ocean is full of intraseasonal timescales as well, and we'll continue a little bit more about this in the next podcast, look at air-sea interactions and so on. Okay.